LEDs are much more efficient than many other light sources, including incandescent light bulbs. However, LEDs still generate heat which needs to be dissipated from the light source during regular operation. This is very important because the long-term reliability as well as the performance of LEDs depends strongly on the temperature in the application. Therefore, it's very important that customers design their thermal management system accordingly to dissipate all the heat which is generated during regular operation. In order to estimate how much heat is generated by an LED, I would like to introduce the concept of luminous efficacy of radiation. Luminous efficacy of radiation, LER, is defined as the ratio of the luminous flux emitted by a light source divided by the radioemitting power of that same light source. In this graph you can see three different lines, a blue line which corresponds to the actual spectrum of a light source, in this case it's an LED light source. If you calculate the surface area underneath this blue line, you get the radioemitting power, how much raw power is emitted by the light source. Now if you take the luminosity function, which is indicated in green, and you calculate the convolution of that green curve with the blue curve, you get the red curve. The red curve is basically how our eyes perceive a light source. If you integrate the red curve, you get the luminous flux of a light source. So once you have the spectrum of an LED, you can quickly calculate the radioemitting power, you can calculate the luminous flux, and therefore you can easily calculate what the luminous efficacy of radiation is. So we just talked about the concept of LER, and I would like to show you how you can use this concept to estimate how much heat is being generated in an LED. If you know how much light is generated by an LED, its luminous flux, and you know its LER value, you can quickly calculate how much radioemitting power is emitted by the LED. Now, if you know how much radioemitting power is emitted by the LED, and you know how much electrical power goes into the LED, the difference has to come out as heat, as shown in this equation. The typical value for LER of a phosphor-converted white LED is 300 lumens per watt. Now, let's assume you have an LED that emits 300 lumens and consumes 3 watts of electrical power. The total amount of heat can then be calculated and equals 2 watts. Many LED system design engineers are probably familiar with the concept of wall-plug efficiency. Wall-plug efficiency basically defines how well a light source converts electrical power into optical power, as shown in this equation. If you know the wall-plug efficiency of a light source, you can readily calculate how much heat is being generated by that light source. However, this assumes that you already know how much radioemitting power is emitted by your LED. In reality, this quantity is not always known, therefore it makes it much harder to use this concept. If you use luminous efficacy of radiation, you only have to know how much light is being emitted by the light source, and that's something you can easily figure out with the datasheet of your LED. So we talked about wall-plug efficiency and we talked about luminous efficacy of radiation. The interesting thing is that wall-plug efficiency typically shows a huge variation across all the LEDs within the same product category, as shown in this histogram graph. In contrast, luminous efficacy of radiation is very tightly distributed because it's only tied to the color point of your LED and does not depend on the flux bin or the VF bin of the product. Luminous efficacy of radiation and wall-plug efficiency show dramatically different behavior as a function of the operating condition of an LED. This graphic shows the behavior of wall-plug efficiency as a function of temperature on the horizontal axis, and the different colored lines correspond to different drive currents. This example demonstrates that wall-plug efficiency can vary up to 50% depending on how hard you drive the LED. In contrast, luminous efficacy of radiation is pretty much constant across all operating conditions of an LED. This is to be expected because the luminous flux and the radioemitting power of an LED are tightly related to each other. So if I give you a typical value for LER, you can use that value across all operating conditions of the LED, and hence we can easily calculate the amount of heat that is generated by an LED using this concept of LER. Now, you can see that LER is a very natural concept to use when you want to do LED thermal simulations. You can read more in our LER white paper.